Hello, I'm Andy Hoyle, and on behalf of my co-author Maya Robinson, I will present Drought Assessment in a Non-Stationary Climate, Perspectives based on the Southwest and Central U.S. In this presentation, we will describe hydroclimatic behavior over the Southwest and Central U.S. in our observed record and in contemporary and future climate model simulations, and use these regions to illustrate complications concerning the separation of drought from secular changes like aridification for the purpose of drought assessment. Here, drought is defined as a period of dryness resulting in impacts from which full recovery is expected, whereas aridification is defined as the secular increase in dryness from which no recovery is expected. We will also consider how context and assumptions of contemporary climates to mute secular changes due to anthropogenic influences may shape our interpretation of drought assessment in a non-stationary climate. In this presentation, our index for measuring hydroclimatic behavior is October to September soil moisture, which integrates the effect of water input from precipitation and water demand by the atmosphere. Observed soil moisture is estimated from the UCLA Surface Water Monitor, and simulated soil moisture shown later is from the Community Earth System model. Our definition of the Southwest includes California, Nevada, Utah, and Arizona. Soil moisture is shown in standardized departures, which measures the difference from the mean in standard deviations. Southwest U.S. hydroclimatic behaviors from the context of a 100-year soil moisture record that spans 1921 to 2020 indicates large year-to-year fluctuations, and more notably, prolonged periods of dry or wet conditions. Examples of prolonged dry conditions include 2000 to 2022 and 1920 to 1940, and an example of prolonged wet conditions spans the 1980s and 1990s. Since wet conditions in the 1980s and 1990s preceded the ongoing dry period, this gives the appearance of a drastic trend to increasing aridity in recent decades. The Southwest U.S. soil moisture time series since 800 CE from Williams et al. 2022 displays many of the same hydroclimatic features as the 100-year time series shown in the prior slide, except over a much longer time period of record, which provides additional context concerning hydroclimatic behaviors in this region. Amid the annual and decadal variations of soil moisture in this 1200-year record, we see that prolonged Southwest U.S. droughts are a feature of the climate in this region. The pink shading indicates the 822-year drought since 800 CE with similar intensity as 2000 to 2022. 7 of these prolonged droughts occurred in the 800 years between 800 CE and 1600 CE, with the ongoing drought the only example in the 400 years since. The last 40 years in the Southwest U.S. soil moisture record from Williams et al. 2022 indicates another interesting feature. The most recent 22-year drought followed the wettest multi-decadal period on record in the 1980s and 1990s. While this is suggested by the considerably shorter period of record shown in the prior slide, it's more apparent here because of the context provided by a 1200-year time series. On the right-hand part of this slide, we introduce observed precipitation and temperature in a recent climate, taken here as 2000 to 2020, compared to a past climate, taken here as 1920 to 2000. To identify possible causes of the recent low soil moisture in the Southwest. Precipitation was much lower in the recent climate across the Southwest, with values exceeding a 20% decline in some areas compared to the past climate. At the same time, temperatures were much warmer in the recent climate across the Southwest, with values exceeding 1 degree Celsius of warming compared to the past climate. Approximate cause of the low precipitation in the recent decades include behaviors in Pacific sea surface temperatures, while anthropogenic effects have been identified as approximate cause of warm temperatures in recent decades. The recent versus past climate difference maps over the United States also indicate notable features in other areas. A central U.S. area, which includes North Dakota, South Dakota, Nebraska, Kansas, Missouri, Iowa, and Minnesota, experienced much more precipitation and higher temperatures in the recent climate. Precipitation increases in the recent compared to the past climate exceeded 15% over much of the central U.S. region. Simultaneous temperature differences between the same two time periods over this region indicate temperature increases of about 0.5 degrees Celsius. Given the precipitation and temperature differences in the central U.S., the trajectory of central U.S. hydroclimate, as measured by the soil moisture time series on this slide, is remarkably different from the Southwest during 1920 to 2020. Most apparent is what appears to be a linear increase in soil moisture from the 1930s to 2020. The wettest 4 decades based on this metric in the central U.S. all occurred since 1980, while the driest 4 decades all occurred before 1960. Also noteworthy is the Dust Bowl, a drought in the central United States in the 1930s, which lives in historical lore for its exceptional intensity, duration, expanse, and impacts. The Dust Bowl occurred early in the period of record that we show here, which gives the appearance that drought duration and intensity have decreased through time over the central United States. We now consider how context and assumptions concerning the causes of observed hydroclimatic behavior through time could shape our conclusions regarding drought, secular trends, and their effects on drought assessment. Data is key to providing insights on secular trends due to climate change, as well as separating these secular trends from the variability that is consistent with drought, which has a clearly defined onset and recovery. On the one hand, including more data is desirable because it provides additional context for robust characterizations of hydroclimate used in drought assessment. On the other hand, including more data, especially from the past, may include conditions that no longer apply in the present and future climate, which are inconsistent with contemporary drought risk. Here, we illustrate how the application of different assumptions of a contemporary climate, in which we attempt to mute secular changes, may affect our interpretations used in drought assessment. We do so here based on the observed records of soil moisture in the Southwest. Suppose the year is 2000, and we use the prior 30 years to serve as the baseline for drought assessment of the future 10 years. For the Southwest, 1970 to 2000, indicated in cream, was a very wet period in the historical record, and 2000 to 2010, indicated in pink, was a dry period. This would make 2000 to 2010 look exceptionally dry compared to the prior 30-year baseline, even though soil moisture in 2000 to 2010 was generally on par with decades like the 1930s and 1950s. Given large fluctuations in regional hydroclimates noted in our observed record, we often use many realizations of climate models to separate the effects of climate change from natural variability, and to better characterize and understand plausible drought variability. Climate model simulations provide more context compared to observations under the assumption that they are reasonable representations of the climate. It is important to note that no climate model is perfect, and they should be used responsibly. Each climate model realization is forced by the same or similar time-evolving conditions like greenhouse gases and aerosols during a historical period and for future periods, but hydroclimatic variability in each realization is different. Each individual realization of a climate model produces a plausible drought history, while the average of those realizations indicates secular changes because of the greenhouse gases and aerosols, which are mostly anthropogenic in origin. Shown on this slide are two very different, yet equally plausible soil moisture histories for the Southwest U.S. from the same climate model, the Community Earth System model, which indicates the important role of variability in the climate system for shaping the perception of drought and aridification. The soil moisture history for the model realization shown in the top panel is more in line with what we observed in the last 100 years. That is, prominent low soil moisture from 2000 to 2020, which was preceded by wetter decades in the 1970s, 1980s, and 1990s. By contrast, the soil moisture history from the model realization shown in the bottom panel demonstrates very different hydroclimatic behavior compared to the model realization in the top panel in our observed record. That is, this realization indicates pronounced dryness in the 1980s and 1990s, which was then followed by general wetness in the 2000 to 2020 period. The phasing of dryness and wetness in this climate model realization gives the impression that drought occurrence decreased from the past to the contemporary climate. This illustration of hydroclimate based on two equally plausible realizations in a climate model is a cautionary tale for assuming the role of climate change in secular trends. According to climate models, the climate change effect is indicated by the average of many realizations of the climate shown as the black line in both panels. The black line indicates a downward trend in soil moisture from the late 1990s through 2020, which then further declines beyond 2020 all the way to 2050. That said, the anthropogenic effect in these models produces aridification amid rising temperatures, as we have come to expect. However, the apparent aridification is much more subtle compared to the year-to-year and decade-to-decade variability consistent with drought, as indicated by observations and model simulations. I will conclude with 3 points. The first is that a long enough history should be considered in drought assessment so that we may robustly contextualize drought. In the case of the Southwest, hydroclimatic variability is complex, and as much information needs to be considered as possible. The second is that we need to make appropriate assumptions regarding climate stationarity to remove secular trends. From what we showed in the prior slides, secular trends are much smaller than the variability consistent with drought over the Southwest U.S. And finally, an informed separation of secular trends and natural effects are key to contemporary and future drought assessment in the Southwest U.S. Thank you.